Welcome back. In this video, we're going to start looking at the Chem 110 ebook, Chapter 9, and exploring valence bond theory. We're going to delve into potential energy curves, how to interpret them, and what they mean in terms of bond lengths and bond strengths. And then we're going to start talking about how atomic orbitals do not readily explain the molecular geometries that we see in our three-dimensional molecules. So a potential energy curve looks at the potential energy of the interaction of two atoms as a function of the distance between their nuclei. So in other words, what we can do when we look at these potential energy curves is see the bond strength, we can see the bond length, we can see what happens as the atoms are brought closer to each other or taken farther apart. And so looking at this graph, we see there's a few questions that we want to address. What do each of the distances signify? So this distance down here, we refer to this as the bond length. The reason for this is because this is the distance at which the nuclei are most stable, interacting with each other. Remember that what we have here in the case of a hydrogen molecule is two protons and two electrons interacting with each other. The electrons repel each other and the protons repel each other, but the electrons and protons are attracted to each other. So there's a very important balancing act that must be determined to maximize the attraction between the protons and the electrons while minimizing the repulsions between the like charges. That happens to be at a bond distance or at an internuclear distance of 74 picometers. What we can see as if we were to take those atoms and put them closer to each other, that the energy would go up, eventually approaching infinity. And that's because the repulsion of the nuclei greatly outweighs the attraction of the nuclei to the electrons at that point. If we go at a distance beyond our bond length, we can see that the energy also goes up. But in this case, it approaches an energy value of 0. That's similar to what we saw when looking at the Bohr model, where the energy of attraction, the potential energy of the attraction of an electron to the nucleus goes up. It gets closer to 0 as the distance increases. The well depth here signifies the bond dissociation energy. This is the energy required in order to break the bond between the two hydrogen atoms. And as we saw already, as we move the particles closer to each other, to the left of the bond length, the energy goes up, going past 0 up to positive energy levels, which means then that this is repulsion, whereas anything below 0 is technically attraction. Let's now take a look at a specific problem. Consider the carbon-carbon single bond in C2H6 and the carbon-carbon double bond in C2H4. Which of the plots shown below best represents the potential energies of these two bonds as a function of their internuclear distance? I think that you're prepared enough to try this on your own, so pause the video and see if you can reason through this one, and then come back. Welcome back. How do we make this kind of a distinction? Well, what do we know? We know that double bonds are shorter and stronger than single bonds. Thus, if we're looking at a double bond, the bond length, which is indicated by the bottom of the well, should be smaller than for the carbon-carbon single bond. When you look at the bond lengths, we can see that in this case, this is saying that the carbon-carbon double bond is longer. We know that that's not true. And we see the same thing here. In D, this is also saying that the carbon-carbon bond is longer than the carbon-carbon single bond. So we know those cannot be true. So both for B and C, it's depicting a carbon-carbon double bond that is smaller, shorter than the single bond, which is good. But which one is stronger? Well, we know that the height of the well or the depth of the well is indicative of the bond strength, as we saw. That's our bond association energy. So because carbon-carbon double bonds are stronger than the single bonds, they should be at a lower potential energy. So in C, we're depicting the carbon-carbon bond that is shorter and stronger than the carbon-carbon single bond. Let's now turn our attention to the formation of bonds and how elements form bonds with each other. So what is it that happens in order to form a bond? We talked about how electrons, they behave as waves, and therefore we describe their location and energies using atomic orbitals. We talked about s orbitals and p orbitals, d orbitals and f orbitals. And for the purposes of Chem 110, when we talk about forming bonds, covalent bonds, we're going to talk about elements whose valence electrons are in the s and p orbitals. So when we form bonds through the valence bond theory, we look at how atomic orbitals overlap with each other, and that shared overlap we would call the bond. Because we're talking about covalent bonds and the sharing of electrons, this overlap of shared electron density or orbitals we call a covalent bond. In Chem 110, Chem 112, you'll learn about what is called molecular orbital theory. So we're not going to discuss it, but the molecular orbital theory, or MO theory, also describes a way of looking at how bonds are formed. There's two types of covalent bonds that you need to be aware of. The first is what we call sigma bonds, and that is the lowercase Greek letter sigma. This results from when you have two orbitals that interact with each other head on. So what that looks like could be any of these three types of scenarios, where we have s orbitals overlapping head on, an s and a p orbital overlapping, or two p orbitals overlapping. Remember when we talked about orbitals that for p orbitals, they have two lobes. And in order to form a bond, those lobes that interact with each other must be in the same phase. So when we've talked about wave functions and waves in general, how in order for them to add together, they must have constructive interference. That's what's going on here. This is looking at constructive interference. I'm going to write it down here because we're about to show something up above. Constructive interference. In this case, when we have sigma bonds, the electron density is symmetric around the internuclear axis. Another way of thinking about this is that you can draw a line in between the nuclei, and that's where the orbitals are overlapping. They're overlapping along the line in between the nuclei. This is in contrast with what we call pi bonds, and this results from the sideways overlap of orbitals. So this only occurs in the case of p orbitals, and you can see that where those orbitals are overlapping is not along the axis of the nuclei themselves, but up above and below that internuclear axis. We'll learn a lot more about pi bonds in a later video. So how can we use atomic orbitals to explain the observed molecular geometries? Let's talk about a simple molecule, methane. We know that methane has 4 electron domains. Because it has 4 electron domains, it's tetrahedral. And therefore, its bond angle should be 109.5 degrees. This is a 3-dimensional structure, and all of the bonding domains are of equal length, equal strength. If we look at the valence electrons of the carbon atom, we see that it has 4 electrons in its valence. We know that because it's in the group 4, and 2 of those electrons are unpaired. Now, when we are forming covalent bonds, what happens is we have the orbitals which overlap, and so if they have the one electron from each orbital, they will combine, overlap, and we will have the electrons with opposite spins sharing that electron density, and that's our covalent bond. So if we look at methane and its valence electrons and the ones that are unpaired, we would actually predict forming a molecule that looks kind of like this, where we're using the electrons in the 2 different p orbitals to interact with the 1s orbital on the hydrogen atom. That's because the hydrogen atom has only 1 electron in the ground state. It's in the 1s orbital. So we'd end up with then covalent bonds, and then these would be our 2s orbital electrons that would be left over as a lone pair. And if we only use the unpaired electrons to form the bonds, in this scenario, we would not have a complete octet on carbon. And our bond angles would be 90 degrees from each other. So the overlap of atomic orbitals does not adequately explain our molecular geometries. So what does? We're going to address that question in our next video. Thanks for watching.